Good morning, students. Magnetism. In last lecture, we have discussed some equations. Okay. Now in this lecture, we will see some questions. See. And first question: an iron rod of length L and magnetic moment M is bent in the form of semicircle. Now its magnetic moment will be. See. Solution of first one. An iron rod of length L. Suppose it is one iron rod of length L. Okay, it behaves as magnet, so it has some constant that is P, and its length is L. So for this iron rod, I say its magnetic moment M is equal to it is P, that is pole strength, and distance between two poles, that is length. So M is equal to it is P. Now this rod is bent in form of semicircle like this. In form of semicircle like this. But see, pole will remain here at this point. So now what is distance between two poles? If radius of this semicircle is r, and radius of this semicircle is r, then what is distance between two poles in case of semicircle? Distance between two poles in case of semicircle, it is 2r. Yes, it is 2r. So how to write? In this case, magnetic moment and this is equal to it is P into 2r. But what is value of r? See, this wire is bent in the form of semicircle. So I can write okay, L is equal to what is length of semicircle? It is half of 2 pi r, which is pi. So r is equal to it is L upon pi. So put here L is equal to it is R is equal to it is L upon pi. Now PL is equal to M. So is equal to it is 2M upon pi. Yes, it is 2M upon pi. So it is the answer of first question. Okay. Okay. What is magnetic moment of this semicircle? Simple. Okay. Yes, it is visible now. Chalo. Next question. A wire magnet of length 3 meter has points A and B along its axis at distances of 24 cm and 48 cm on the opposite sides. Okay. Ratio of magnetic fields at these points. Ratio of magnetic fields at this point. It is actually 3 cm. Okay. It is actually 3 cm. So see here, as this 24 cm and 48 cm, they are given distances. This distance is greater than its length. We can say 3 is small with comparison to 24 and 48. So we can say it is short magnet. Okay, short dipole, or you can say R is very greater than L. So in such case, what to do? See, you are given a paramagnet of length 3 cm. It is paramagnet. It is its axis from this center A and B along its axis at distances of 24 cm and 48 cm. Suppose A is here at a distance 24 cm and B is here in opposite direction at distance 48 cm. Okay, so you have to find what is ratio of magnetic fields at this point. So see, we know that as A and B are on axis, what is equation of magnetic field on axis? It is mu 0 upon 4 pi 2m upon r cube. 2m upon r cube. Now mu 0 constant, 4 pi constant, 2 constant, m magnet is same. Okay, so magnetic moment is also same. Distance changes, so we can say A is proportional to 1 upon r cube. Okay, so now if we want to write equation for this A and B, then I can easily write like this: A magnetic field at A and magnetic field at B is equal to, here it is as inverse relation. I can write it is what is distance for this point B? It is 48. What is distance for this point A? It is 24. Okay. Simple. Okay, so 24 into here it will be 2. So it is PA divided by AB is equal to 2 cube means it is 8. 2 cube means it is its answer. Clear? Okay. Next one. Number 3. Check what is number 3. You are given two magnets, and due to these two magnets, you have to find what is direction of magnetic field at point P. The direction of resultant magnetic field at point P is blank. So first of all, okay, suppose you are given one bar magnet, okay, like this. If it is one bar magnet, it is its north pole, it is its south pole, okay, it is its axis, equator. First of all, we will see electric field lines due to a bar magnet. Okay, on axis magnetic field, it is magnetic field line. It is like this. Magnetic field line is like this. Okay, another magnetic field line, it is like this. From north outside, in south inside, like this. Okay. Magnetic field lines of bar magnet. Magnetic field lines of bar magnet. Now you have to remember characteristics of magnetic field lines, that magnetic field at each and every point is in direction of tangent at that point. Yes, magnetic field at each and every point is in direction of tangent at that point. We also know that magnetic moment, its direction is from south pole to north pole. Yes, it is in direction of south pole to north pole. So on axis and on equator, if we want to find direction, we have to simply draw tangent. For example, it is axis. So at this point, if I want to find direction of magnetic field, so obviously it is in this direction. It is direction of magnetic field on axis. Again, if I want to find direction of magnetic field at this point, so see this arrow represents itself magnetic field on axis. Magnetic field on axis. Simple. If I want to find magnetic field on equator, so at this point equator, if I draw tangent, it will be in this direction. So it is direction of magnetic field on equator. At this point also, direction of magnetic field on equator. That is magnetic field on equator. So you can simply say, okay, magnetic field on axis and magnetic field on equator, they are in opposite direction. They are in opposite direction. Okay, see this magnetic field on axis, that is VA, it is in direction of magnetic moment M. But this BE, it is in opposite direction of, it is in opposite direction of, yes, it is in opposite direction of. In this case, how to find direction of magnetic field? So see here, it is first magnet, it is the second magnet. As it is south pole, north pole, here it is south pole, it is north pole. At point P, yes, from figure we can easily say, okay, this point P is on axis of this magnet, on axis of this magnet, and in south pole magnetic. Due to this, first of all, you have to draw some picture, okay, due to this one. So at point P, due to south pole, okay, magnetic field will be in this direction. So that is due to this one, due to this two. Okay, we know that from north pole magnetic field outside and south pole inside, in direction of tangent. In direction of tangent. So due to this magnetic field at this point P, it will be in this direction. That is B. It is in this direction. So yes, we have to draw only direction. That is due to first magnet, B1 in this direction, due to second magnet, B2 it is in this direction, and we know that if these two magnets are identical, okay, B1 and B2 they will be same, and the resultant will be exactly like this. It will be resultant magnetic field B. It will be resultant magnetic field B. So yes, you have to find only this. In which direction is the resultant magnetic field? In which direction? That is resultant magnetic field. Clear? So yes, this direction you have to remember. Okay, magnetic field on axis, it is in direction of M. It is in direction of moment. And then BE, that is magnetic field on equator, it is in opposite direction of magnetic moment. Clear? So yes, these three questions, okay, basic questions. Yes, just you have to remember, okay, what is figure, how to find direction of magnetic field on axis and on equator. Clear? Okay. Now we will see next questions. Okay, now we will see two questions as a combination of magnets. See, two identical magnets are shown in figure 1 and here it is 2. Under the influence of magnetic field produced by magnet 1 and magnet 2, one needle which is placed at this point aligns in this direction at angle theta with vertical. Yes. Okay. Your question is, you have to find d1 upon d2. What is ratio of distances d1 upon d2? This needle, it is right now in equilibrium. Right now it is in equilibrium. The resultant magnetic field is in this direction. It aligns at angle theta with vertical. Now there is one simple calculation of this question actually. This needle is on axis of this first magnet and on equator of this second magnet. So magnetic field due to this first magnet on this needle I will find. Okay, magnetic field due to first magnet, V1, as it is on axis, you can write on axis. Okay, V1 is equal to, it is mu 0 upon 4 pi 2m upon d1. Simple. Identical magnets, I have assumed the magnetic moment is m. Now, what is direction of this V1? From northward, magnetic field is outside. So, due to this magnetic field V1, it will be in this direction. It is magnetic field V1. Here it is resultant. Okay, resultant you are V1. Okay, I have calculated this V1. Now, similarly, magnetic field due to second magnet, and due to second magnet, needle is on equator. So, magnetic field due to second magnet which is on equator, B2 is equal to mu 0 upon 4 pi. On equator we have equation that is m upon B2. Identical means the magnetic moments are same. Distance given here it is d2q. And now what is direction of magnetic field? As we have discussed, direction of magnetic field on equator, it is in opposite direction of magnetic moment. It is P2, it is in this direction. From north to south, like this. Okay, so direction of V1 and here it is direction of V2. So yes, two directions, V1 and V2, they are shown in figure. Okay, now we know that this V is resultant of V1 and V2. V is resultant of V1 and V2. Okay, and this V makes angle theta with this V2. Hana? Yes. So how to write this? See, yes, actually we know equation of theta. That is y component upon x component. But in this question, what happens? As theta is making angle with this B2, as theta is making angle with this B2. How to write? So see, B1, I can draw here it is B1. Here it is B1. So if you apply tan theta means, hello, tan theta means it is opposite side upon adjacent side. So from figure you can say that tan theta is equal to it is B1 upon B2. Tan theta is equal to it is B1 upon B2. Simple. Any doubt? Okay. So therefore B2 tan theta is equal to B1. Now put value of B2 and B1. B2 you 0 upon 4 pi n d2 cube tan theta is equal to d1 means u0 upon 4 pi 2n d1 u0 4 pi u0 4 pi n m cancel out. Simple. As you have to find ratio of d1 upon d2, so you can say d1 cube upon d2 cube is equal to yes. d1 cube d2 cube here it will be 2 divided by it is tan theta. And so you can write d1 cube upon d2 cube is equal to 2 cot theta. So d1 upon d2 is equal to 2 cot theta raised to 1 by 2 cot theta raised to 1 by it is how to solve question. Okay, so yes, it is the one question and its answer as shown in the figure. Okay, so yes, it is this. Now next question. See. Now next question. Again, you are given two bar magnets placed perpendicular to each other, and yes, they are short bar magnets. Okay, short magnets of equal dipole moment m. You have to find magnitude of magnetic field at distance d from the center on the bisector of the right angle. On the bisector of the right angle means, see, angle between them is 90. On bisector means at this point, if it is this point B, at this point you have to find what is magnetic field. Now this point is not on, this point is not on axis, not on equator. Then how to find? See, yes, you are given two magnets. Its magnetic moment m, it is in this direction. Okay, or I can say this m1 is equal to m. Its dipole moment, it is in this direction. So I can say m2 is also equal to m. So if I find what is resultant magnetic moment of this two, means what is resultant magnet due to this two. And to see what happens. Here it is. Okay. Resultant magnetic moment. M dash is equal to, it is m1 plus m2. As m1 and m2 are perpendicular to each other, I can say that m dash is equal to this under root m1 square plus m2 square plus 2 m1 m2 cos 90. Cos 90 is 0. So just m dash is equal to this under root m square plus m square. So m dash is equal to it is root 2m. M dash is equal to it is root 2m. Now I can draw the equivalent figure like this. See, m1 it is in this direction, m2 it is in this direction, and they both have same magnitude. According to law of parallelogram, if two vectors have same magnitude, then their equivalent is on its bisector at right angle. So yes, what is equivalent of this two? Equivalent of this two is one magnet. I can say like this, having south pole this side, north pole this side, and its magnetic moment m dash in this direction. This m dash in this direction. Now as this point is also on perpendicular bisector at distance d at point P, now you can easily solve. Here, what is meaning of this question? Hello, do you understand? Magnetic moment due to this, magnetic moment due to this, the resultant magnetic moment is this, and yes, the resultant magnetic moment it is in this direction, because they both have same magnitude. Same magnitude means if it is vector A, it is also vector A, then their magnitude will be completely here. Okay, this two angle becomes 45 degree, it is also 45 degree. Yes. Okay, this perpendicular bisector is 45 degree. Here it also becomes, here it is 45 degree. Okay, so now this point is on axis of this magnet, resultant magnet. Okay, the point P is now on axis axis of resultant magnet having magnetic moment and dash. Having magnetic moment and dash. And what is equation? Yes, P is equal to mu 0 upon 4 pi 2 m dash upon dq is equal to mu 0 upon 4 pi 2. So what is value of m dash? Is root 2m. So it is root 2m upon dq. It is your answer. Okay, so it is how to solve such questions regarding magnets, combination of magnets. Okay, actually you have to remember equations only. Okay, if you remember equations, then you can easily solve such questions. Simple. Okay, so yes, I think this is it for today's lecture. In next lecture we will continue some new questions. Till then, tada.